continue on with our few words about waves, part 2. We need to talk about a couple of key concepts here. One known as the phase of the wave, and leads us to the concept of interference and constructive and destructive interference. This is going to be key, as we'll probably talk about actually in the next video clip, with a famous experiment that was done a few years before Einstein's time that really put a wrench in the works for physicists. They could not figure out what to do with the results of this experiment, and it was called the Michelson-Morley experiment. So we're leading up to that, getting the concepts down. We need to understand not only Einstein's principle of light constancy, but also how to understand this so-called Michelson-Morley experiment. And interference will be a key concept there. So let's take a look at it. Let's say we have two waves. We can imagine they're water waves. Again, later on, of course, we'll be imagining they're light waves. Either one will work in this case. And so here's wave number 1. Here's wave number 2. The concept of phase means that as you compare them, say they're traveling along side by side here, then they're in sync with each other. The peaks match up, the troughs match up. And in this case, pretty much exactly. So we'd say those two waves are in phase with each other. In a minute, we'll do an out-of-phase situation, but you can probably guess that just means then things don't line up if it's out of phase. And then you can also ask the question, well, how much out of phase is it? Well, let's do the in-phase case first. So we've got our two waves, the way I've drawn them, more or less. Limits my artistic ability here a little bit, but try to get them synced up. So the peaks and troughs are all lined up together. And so again, imagine two water waves maybe traveling side by side or maybe just angled slightly so they're about to come together. And what will happen is if they're in phase with each other, if the wavelengths are the same and the frequency, the period, and everything is in sync, as it were, the peaks and troughs are in sync with each other. As they come together here, the waves are going to combine, and the peaks are going to get even higher and the troughs even lower. In other words, what happens is the peak parts add, the trough parts add in a sense, and everything else adds along here as well. So the combined wave then is going to look something roughly like this. We're going to, if these are the same height, the same amplitude, we're going to double it then. So it might look something like way up here, and then way down, and way up, and way down, and way up again, more or less. And if we draw the center point line there, not quite, in terms of my diagram here, maybe not quite exactly double, but that's the concept, that the two peaks add, the troughs add, and so the amplitude increases then. Remember, the idea of the amplitude is the distance from the highest peak to the center point there, or also the lowest point there. And so this is known as constructive interference. The waves are interfering with each other, coming together, they're adding together, but they're doing it constructively. Okay? In other words, the peaks add, and you get bigger peaks, and the trough sections add as well, and you get deeper troughs that way. So that's known as constructive interference. And so, again, in a bathtub situation, a water tank, or a swimming pool, something like that, if the waves are in phase with each other, they start adding together, you get even bigger waves going on that way. And for light waves, you get brighter spots. You get an increase in the intensity of the light. So that's constructive interference. What about destructive interference? So let's do that situation here. We'll get rid of our combined wave. And actually, we're going to get rid of wave number 2. We need a different version of the wave. In fact, before we get rid of it, let's just think about what's going to happen. Now we're going to draw the second wave so it's out of phase with the first wave. Our first example here, they're both in phase. In fact, exactly in phase with each other. So everything added together. They combine, we get constructive interference. Now we're going to draw it the second way so it's exactly out of phase with it. And in the terminology, again, for those of you who might have had a little physics before, maybe even just heard it, because it's sort of a common term. It's 180 degrees out of phase. Why it's 180 degrees, we won't go into that, but you may have heard that term before. So it's exactly out of phase with it. So wave 2 then is going to look something like this. Where we have peaks, we're going to have troughs. Where we have troughs up here, we're going to have peaks. And so if I can channel my, I don't know if this would even be anything close to Picasso, but let's see, I'm already off here. Try this again here. Okay, something like that. Maybe a little too big in terms of some of my troughs here, a little too deep. Okay, so hopefully you can, in your mind, fix all the inconsistencies there. But the big thing we're after here is we see the trough of this wave is matched up with the peak here exactly. The trough here is matched up with this peak, peak, and so on and so forth. So now you imagine these two waves. Again, water waves maybe traveling next to each other, coming together to an intersection point up here. If they're exactly out of phase, when this one has a peak coming in, this one's going to have a trough, and they cancel each other out. And you get just still water at that point. And if you have a trough here, but a peak is coming in here, they're going to cancel each other out, and you get still water at that point. So when you have destructive interference, when the two waves are exactly out of phase with each other, the combined wave is simply this. I think I can handle drawing that, more or less straight there. Okay, so destructive interference, you end up with no wave at all. You had two waves coming in, and again, we're assuming that the wavelengths of the two waves are the same, so everything matches up nicely, and so on and so forth, and the amplitudes are the same. And everything cancels out exactly. Now you might say, well, what happens if the amplitude of wave number 1 is greater than the amplitude of wave number 2? So in other words, this peak is bigger than that trough is deep, or this trough is deeper than that peak is tall. Well, you'll still get destructive interference, but this wave will not completely cancel out that wave. And so you will be left with a little wave after that. You won't be left with nothing at all. Okay, so that's the concept of destructive interference, constructive interference and destructive interference. And as we will see, as I mentioned a few minutes ago, this is going to be the key concept in understanding the Michelson-Morley experiment, and then beyond that, understanding why it was such a big deal for the ideas in the special theory of relativity and what effect it might have had on Einstein himself in terms of his thinking about the special theory of relativity. Okay, so that's a few more words about waves, part 2. In the next section, we'll actually have even a few more words about waves, so we'll get on to that in just a few minutes.